Welcome back, nerds. Moving on to section 2.4 today. We're going to be manipulating our exponential functions now. Yay, manipulations and transformations. We are going to do manipulations and transformations, well, manipulations specifically using rules of exponents, things that you learned about in Algebra 2, and you actually learned about some of them in Algebra 1. But just to remind you what's going on here, these are all things you should already be comfortable with. But what we got going on is, as long as A and B are both positive, because we're talking about exponential growth, specifically functions, I guess, know that a product raised to a power just gives that exponent to both A and B. It's not distribution. It's like application. You're going to make sure that both the A and the B get that exponent. This one says a power to a power. When you have a power raised to a power, your job is to multiply those exponents. But since the order of multiplication doesn't matter, I could also write it like this. I could switch the exponents. And that's very useful when manipulating exponential functions. We already talked about this when we did it yesterday, actually, and we'll do it some more today. But it says when you multiply two numbers with the same base, you add their exponents. It's not on here, just reminding you when you divide two numbers with the same base, you subtract their exponents. But that's not on here because it's not really useful for manipulating exponential functions. That's why it's not in this box. We did this one yesterday, but just reminding you, if you have a fractional exponent, the denominator is the root type. So if it says the 1/2 power, square root, 1/3 power, cube root, so on and so forth. This one's really useful to us when manipulating exponential functions, especially in reverse order, going from this side to this side, because then we can describe it using transformations. But what it says is, if you want to move something across a fraction bar, just change the sign on its exponent. So if you have a negative exponent, you could move it to the bottom of a fraction bar. Now the exponent's positive. Or if you had something down here with a positive exponent or a negative exponent, it doesn't matter, and you want to move it across the fraction bar, then you just change the symbol on its exponent. So if it's down here with a positive exponent, you can move it to the top with a negative exponent. And lastly, basically the same property as that. But instead of saying a product to a power, we have a quotient to a power. Both the top and the bottom get that exponent. Alrighty? All that is old Algebra 2 review. The first 3 examples here are legitimately straight up and down, grab a calculator style questions. We're just going to round everything into 3 decimals because this is AP. So 5 raised to the 2.3. I have no idea how to do that by hand. Luckily, we have a calculator boop, to give us our answer. 40.516. 3 raised to the square root of 7. Oh my golly, I don't even know what the square root of 7 is. How would I possibly know what 3 raised to the square root of 7 is? $18.295. And 6 raised to the negative 1.5. Really small number. To 3 decimals, 0.068. Okay, well, those are easy peasy, right? We won't need our calculator again today. That was it. Just make sure that you know how to use your calculator to evaluate stuff. So we're going to step away from exponential growth and decay functions today, and we're just going to be talking about exponential functions in general. So what we have here in this box is information about the parent exponential function. So no vertical stretch or shrink, no vertical shifting, no horizontal stretch and shrink, no horizontal shifting, literally just a number raised to the x power. And it doesn't matter what the base is. All parent exponential functions based to a power will have these things in common. First of all, because b is a positive number, you can raise it to any number you want to. Who cares? Raise it to anything you want. Domain, all real numbers. And since b is a positive number, raising it to any number you want is going to result in another positive number. You'll never get to the value of 0 because a positive number raised to a number could never be 0. You can get really close to it, or you can get really far away from it. And that is why the range is all positive numbers, 0 to infinity, not including 0. All parent exponential functions will go through the coordinate 0, 1. Why? Because b raised to the 0 is always going to be 1. So all parent exponentials go through 0, 1. That makes the y-intercept 1 for all of them. And we have two different cases. We have the case of our exponential base being greater than 1, which is a growth function. It's increasing, continuous, and concave up. I'm going to sketch that for you. Whee! There you go. Increasing, continuous, concave up. Just reminding you what increasing means. Increasing means that all of the rates of change are positive. Cool with that? Yeah? Okay, just reminding you what concave up means. The rates of change are increasing. Or you could say the rates of change of the rates of change are positive. If you wanted to use first and second differences. Increasing means first differences are positive. If you want to use first and second differences, concave up means the first differences are increasing, or you could say the second differences are positive. That's all stuff from Unit 1. Now, if we have an exponential base that's between 0 and 1, remember it can't be 1, because if it was 1, you'd have 1 raised to, well, who cares what you get, because every y value would be 1. It's a horizontal line. But the other case is the base is between 0 and 1. This gives us an exponential decay graph. Exponential decay graphs are decreasing. They're continuous. And they still concave up. How about that? But they look like this. Decreasing tells us that all of our rates of change are negative. That's the same thing as saying your first differences are negative. And we've already mentioned what it means to be concave up. Concave up means the rates of change are increasing, or you could say the first differences are increasing, or you could say the rates of change of the rates of change are positive, which is the same thing as saying the second differences are positive. Okay? Just saying all the different ways. Now, both of these graphs, I drew a red dotted line, and that's because the graph will always approach but will never actually cross the x-axis. So for both of these things, the red dotted lines are the x-axis. The x-axis is the line y equals 0. It is a horizontal asymptote because a positive number to any number will never equal 0. And both of these are functions. Both of them, if you turn sideways, you see their inverses are also functions. That means they're both 1-to-1. We haven't really talked about this here, what it means to be 1-to-1, and I don't know how important that is for AP. I have to look into it. I imagine if it was a big deal, it would have been in Unit 1 when we were doing all the graphing stuff. But there you have it. All that stuff, true for b to the x. So we're going to graph two different things, and I'll use two different colors. I'll use blue for f of x, and I'll use green for g of x. These are both b to the x style graphs, so they're both going to approach the x-axis, y equals 0, horizontal asymptote. I'm not going to make a point tree. I'm just going to talk about what happens if you plug the numbers in, all right? Let's see. Forgot to do attendance. There. Well, it's b to the x, so it's going to go through 0, 1. But that's because 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. Oops. 2 to the 1 is 2, excuse me. 2 to the 2 is 4. 2 to the 3 is 8. And 2 to the 4 is 16. Man, this thing got really tall really fast. Ignore this dot. It shouldn't have been there. If you wanted to go to the left, you could say 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. You're just going to get closer and closer and closer to that x-axis. I am better at drawing exponentials when the paper's sideways. I don't know why. So I'm going to turn my paper sideways. There we go. Now we're going to do the same thing for the green graph. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 to the 2 is 1/4. Crud. As I go to the right, this thing gets closer and closer and closer to the x-axis. So let me go to the left. 1/2 to the negative 1. That's 2. Because remember what a negative exponent does. It moves something across its own fraction bar. So if you said 1/2 to the x, you're actually saying 1/2 to the x. So if you use x equals negative 1, you have 1/2 to the negative 1, which is just 2 to the 1. Using the same logic, 1/2 to the negative 2 is 4. 1/2 to the negative 3 is 8. 1/2 to the negative 4 is 16. And again, I draw my exponentials better sideways. What do you notice about these two graphs? What do you see? Yeah, they're reflections of one another over the y-axis. Allow me to use some properties of exponents to manipulate the equations to show you why that was the result. Let me take my 1/2 to the x power. Do you remember when I told you sometimes it's beneficial to move something across its own fraction bar, even if it's going to make the exponent negative? This was one of those times, because if I wanted to say that was 1/2 to the 1, but I want it to look like a reflection, what I could do is I can move that 2 to the top of its fraction bar. And now the exponent is negative 1. And when you have a power raised to a power, you just multiply the exponents. And as you can see, they're the exact same equation. One has positive x, the other has negative x. And if you remember back to way back in chapter 1, the beginning of the year, replacing x's with negative x's, reflection over the y-axis. Pretty neat, huh? Ain't that cool? Now, in case you have forgotten all of the Hyovoss transformational rules, here they are. In case you didn't remember, adding or subtracting on the outside of the function, that's shifting up and down, vertical, outside, same. So adding a number on the outside shifts up, subtracting a number on the outside shifts down. Mr. M, you keep saying inside, outside. What does that mean when we're talking about exponential functions? The inside is the exponent. It's where the x's are. So wherever the x's are for any function, that's going to be your inside. So for exponentials, it's the exponent position. So if you have addition or subtraction in the exponent position, this is you shifting left and right. But remember, horizontal inside opposite. So subtraction in the exponent is actually shifting to the right. Addition in the exponent is actually shifting to the left. Multiplying on the outside, which would be in front of your exponential, is always going to result in a vertical dilation of some sort. And I'm pretty sure we don't have to know stretch and shrink. We just have to know, is it a vertical or horizontal dilation? And then by what number? Cool with that? So you got a multiplication on the front. You could say this is a vertical dilation factor 3. This is a vertical dilation factor 1/2. What you're always going to have to remember, though, is you're only looking at the absolute value of that multiplier, because a negative sign is always a reflection. Negative sign on the outside, reflect over x-axis. Negative sign on the inside, that means in the exponent position. Reflect over y-axis, which is what we just saw. Don't worry, I know I hopped over it. I just wanted to mention why it says absolute value. What about multiplication in the exponent? If you see multiplication in the exponent position, this is a horizontal dilation. Just remember, horizontal inside, opposite effect. We have to use the reciprocal of whatever the multiplier is. So you see a 1/4 in front of your x. Oh, that's a horizontal dilation, factor 4. You see a 3 in front of your x. Oh, that's a horizontal dilation, factor 1/3. I'm pretty sure we don't need to know stretch and shrink. But there it is, all your Highvos stuff that we did at the very, very beginning of the year. Okay, oh no. We're going to graph 3 to the x, and then 3 to the x plus 2 on the same grid. Do them in 2 different colors. What did I graph my 2? What is it, blue and green last time? Okay, blue and green it is. Blue and green sounds good. So we'll do blue for f of x, and when we get to it, we'll do green for g of x. Oh, that's fun, green, g of x. No, just me? Okay. Anyway, 3 to the negative 2, that's 1/3 squared, 1/9. 3 to the negative 1, that's 1/3. 3 to the 0, 3 to the 1, 3 to the 2. There they be. Both of these are exponential functions that do not have a vertical shift. So because there's no vertical shift, they are both going to approach the x-axis. I'm not going to try to plot negative 2 comma 1/9. It's darn near on the x-axis. Okay. Negative 1 comma 1/3. I mean, I could try to do that's like right here-ish. 0, 1, 1, 3, 2, 9. Yikes. That's way up there at the top. And again, I do a better job when they're sideways. And even then, it's not a very good job. So could you imagine if I had to do it the other way? Ta-da! There is f of x. For the next one, I have to add 2 to the x value before I evaluate. So if I add negative 2 to 2, that gets me a 0. So this actually says 3 to the 0, which is positive 1. So I have a coordinate at negative 2 comma 1. That's here. Then negative 1 plus 2 is 3 to the 1. That's 3. So I have negative 1 comma 3. Adding 0 to 2 gets me 2. 3 to the 2. So 0 comma 9. Oh my goodness. I'm kind of out of graph. But I think you can see what's happening. 1, 3, 9. It's multiplying by 3 each time. 27, 81. Oh my golly. Look at that. You know what would have been easier than actually finding all these values? No. Just shift all your coordinates left 2 units using transformations. Look, take your y-intercept, shift it left 2. Boop, boop. This one, left 2. This one, left 2. That would have been even easier. Just shift all their dots left 2. So that's how you would describe that transformation. Shift left 2 units. But look at this next example. It says show that it could have been written like this. Okay. Remember when you multiply two numbers with the same base, you add their exponents? That means I could change this to 3 to the x times 3 to the 2. And that's 9. So 9 times 3 to the x is the same as 3 to the x plus 2. They're the same graph, the same equation. So we can either say shift left 2 units or we could have described this. That's a vertical dilation, factor 9. They're both true. Isn't that neat? That a horizontal shift can be written in terms of a vertical dilation? I think it's pretty cool. I really like that. That one kind of transformation can be written in a different kind of transformation and get the exact same result. I like that a lot about exponentials. Questions, comments, concerns, or is it making perfect sense and is easy peasy? One person says it's good. Okay. Then I guess I'll move on. Alrighty. I guess I'll just keep graphing in blue and green. All right. F of x. 2 raised to the negative negative 2. Oh, that means 2 to the 2. 4. 2 raised to the negative negative 1. Means 2 raised to the 1. 2 to the 0. 2 to the negative 1. 2 to the negative 2. I think we can see what's happening there. We're just dividing by 2 each time, which is the same as multiplying by 1/2 each time. Let's go ahead and, well, no vertical shifting, so we know that the x-axis, y equals 0, is the horizontal asymptote again. That hasn't changed. Let's plot these bad boys. Negative 2 comma 4 is here. Negative 1, 2. 0, 1. 1, 1/2. I'm not going to try to get the 1/4 on there. If we wanted to, we could use negative 3 also. 2 to the negative negative 3 is 2 to the 3, which is 8. There. So let me go ahead and sketch f of x. Green for G. This is going to give me 2 to the 4. Oh my golly. Negative 2 comma 16. That isn't even anywhere near possible. That's like way up here. That's way up here. 2 to the 2. I can get that one on there. That's 4. So negative 1 comma 4 is here. And like I said, the other one was like way up here, right? Something like this. I don't know. It doesn't matter. I'm not going to try to connect that dot. Put a 0 on there. I think you can see the pattern. We're dividing by 4 each time, which is the same as multiplying by 1/4. Negative 1 comma 4 is on there. 0 comma 1 is on there. 1 comma 1/4. Well, that's way down here. Look at that. Look what happened here. My graph is underneath the blue graph until the y-intercept. Then it's like that. Jeez. What is going on here? I'll tell you what's going on here. I multiplied my x's by 2. That's a horizontal dilation. Factor reciprocal of 2. Oh, the green graph is half as wide as the blue graph. So what does that do to our coordinates? That cuts all the x values in half. It gets all the x values closer to the y-axis. This coordinate was at -1, 2. Now it's at -1/2, 2. This one was at -2, 4. Now it's at -1, 4. It cuts all of the x values in half. It squishes the graph closer to the y-axis. You say you hate that? Yeah, it takes all the values, it gets it closer to the y-axis because it's horizontally not as wide. No. This time we're being asked to show that this 2 to the -2x can be written like this, where we have some number to the x power. Okay, let's do that. Power to a power, right? Oh, wait. Multiplication in the exponents is a result of raising a power to a power. So I could actually say it like this. But 2 to the -2, that's 1/4. Wait a minute. Wait a minute. Let me go back to this 2 to the -x for a moment. And we apply the exact same trick. Two to the -1 is 1/2. Look at that. Multiplying my x's by 2 is a horizontal dilation of factor 1/2. But I get the exact same result if I double my base. So neat. So neat that changing the base is a horizontal dilation. So what did we see? We saw that addition or subtraction in the exponent could either be described as a horizontal shift or a vertical dilation, depending on how you manipulate it. Multiplication in the exponent position could be described as a horizontal dilation, or it could literally be you changing the base. So changing the base is a horizontal dilation of some sort. That's neat. That's neat. And we've already described it. It's the horizontal dilation factor 1/2. And the last one for today, because I plan on this lesson taking us 2 days, is right here. For the first time, we're going to see a vertical shift. Blue, green. But there's a slight trap in the way these are written. Let's try to graph this real quick. Let's find its y-intercept. When x is 0, what is my y value here? It's not 1. It's -1. And here's why. Only the 2 has the exponent. The negative does not. So the interpretation is that this is written as -1 times 2 to the x, where your a value is -1. The only way that that negative sign gets bossed around by the exponent is if it had been written like this. But those are two completely different things. Just to really prove a point. Just figured I'd show you. So make sure you interpret it correctly. This one, you know what? Let's see. Blue and green, right? Let's do... Well, you know what? I'll just... Let x equal 0, you get negative 1 times 1. Let x equal 1, you get negative 1 times 2. X is 2, you have negative 1 times 4. And x is 3 is negative 8, falls off my graph. If it's negative 1, it's negative 1 times 1/2, so on and so forth. So we're going to get this graph. This is f of x. The y-intercept for f of x is 0, negative 1. Now we could either go through the process of plugging all of those in again and seeing what we get, or we could cheese it and know exactly what kind of transformation this is going to be. What's that going to do? Shift up 3. Which means everything shifts up 3, including the horizontal asymptote. So this coordinate goes up 3, 1, 2, 3. The y-intercept goes up 3, 1, 2, 3, 1, 2, 3. And we can actually get 3 on there now. Negative 8 plus 3, negative 5. Oh, it says label its y-intercept. 0, 2. Because we just shifted the blue one up 3 units. For part B, the very last thing we're going to do today is talk about transformations one more time. And it says compare these things to y equals 2 to the x. So how is f transformed? What do I have to do to y equals 2 to the x to get my blue graph? Reflect over x-axis, because that is me multiplying by a negative 1 on the front. Now the green one is upside down as well. Remember, when you describe transformations that are on the outside, you have to follow PEMDAS, because vertical, outside, same. Follow the exact order you would expect. So you will need to do the multiplication first. Yes. Reflect over x-axis, then shift up 3. What do you guys think? Easy peasy? Good stopping point for today? No questions? Thanks, nerds.